Good evening.
Good evening.
Shall we start now?
Yeah, sure. Talk on. You got it?
Am I audible?
Yeah, you are. Yes. Okay, please go ahead.
Shall we start? The mind. Mom, good evening.
Good morning, ma'am. Shall we start
Never
the session?
attach the mind. Good evening to all of you. I welcome you all. Day 4 validity session of mutual workshop on nanotechnology pharmaceutics
Yes, ma'am.
by 6th of this month.
Yes, ma'am. Monopriya, ma'am.
Organized by Department of Biotechnology, Kapaganaga College of Engineering. I extend my warm greetings to welcome to Dr. T.N. Kurura, Professor, Chemical Design, Indian Institute of Welcome you, sir. I invite Ms. G. Assistant Professor, Department of Technology, to speak.
Hello. Yep. Wait a second. How do I load the? I have the PPT open, but how do I join the PPT to the meeting?
Sir, is there a share presentation option, sir? You can share the presentation.
Let me check. I don't see a share on this.
Present now. Present now, sir. Present now, is it?
Present now. Okay.
Yes, sir. You can share that, sir. Present now.
Yeah, got it. Got it?
Yes, sir. Receiving, sir.
Okay.
Thank you, sir.
Good morning. Good morning to you all from Buffalo, New York, where I'm currently stuck due to COVID. And on polymorphism in solids, pharmaceutical relevance, as I've already indicated. And I just wanted to share with you where I stay, because this is something which is very nice. I live in a place which is in 13 Mallard Court, Amherst, which is my daughter's house, in Buffalo, which is in the western New York region. It's about 10 miles from Niagara Falls. You see the surroundings which are shown up here. So I go for a walk in the mornings in these areas. I even see some animals once in a while, like this one, which is a deer, and it's a very pleasant stay here. So despite the COVID problems, I seem to be enjoying this whole show. And I'm very happy for the invitation given by your college. Particularly, I should thank especially Priya for her interest. And I will now present the talk in the following way. So, as you all know, matter is made up of gases, liquids, and solids. In gases, the particles are not in contact with each other. They are free to move around in all possible directions. And they are in a three-dimensional space. They occupy the entire space. If we take a gas, therefore it's difficult to study the particle in a gas. And so what is done is we have to arrest the particle in the gas by reducing the temperature or compressing it. When we reduce the temperature or compress a gas, it eventually goes, most of the materials go into a liquid form. And in the liquid form, the particles are in contact with each other. However, at any given normal temperature, pressure, and therefore the particles, though in contact with each other, are continuously moving under the Brownian motion. And again, as a consequence of that, if you want to study the particle, it becomes a problem. So we further reduce the temperature or increase the pressure. Eventually, most of the liquids can go into solid form. And in the solid form, the particles are arrested. The points which we should look into this issue of drugs is something very interesting. Most of the drugs are used. In the solid form, and in fact, about 70% of the drugs which are used worldwide are essentially given in the form of a pill or a capsule. So it is important to see the solid form of a drug. So in the formulations of drugs, one has to worry about the way in which a solid can be resulted. One of the advantages in the solid form is that when the particles are arranged in such a way that they form a uniform distribution in all three directions, it becomes a crystal. And the advantage of a crystal is its purity. It's in crystalline forms. There is always an issue of order, disorder in these particles. However, this can be arrested in the crystalline form, and one can in fact study both order as well as disorder as a consequence. The examples of these solids can be seen in terms of the existence of what we call as allotropes and polymorphs. For example, if you look at the allotropic forms of carbon, we have carbon existing in the form of graphite. It exists in the form of diamond. It exists in the form of C70, C60, and other forms. everything is carbon. So a single element which exists in different forms is a consequence of the way in which the atoms are arranged in this solid. For example, in graphite, there is a way in which the carbons are connected to each other in the form of a planar moiety, and therefore it results in a plane. Whereas in diamond, it is a three-dimensional structure. In C60 and C70, the structure gets a little more complex. Just like it happens in elements, it can also happen in compounds. And when in compounds in the crystal form, if they exist in more than one form, these are referred to as polymorphs. Now, why we should worry about solids and crystalline form is because the molecules or particles which are arranged in the solid obey certain rules and regulations. One of the rules, major rules which has to be followed by crystalline moieties is the issue of symmetry. So let me show you some nice pictures to bring in the concept of symmetry. Particularly, this is useful for the graduates and undergraduate students. Look at this picture. What you see in this picture is the translational periodicity that is associated with the repeat unit. Flying horses, we see the white flying horse, we see the red flying horse, and we see the white flying horse again. And you see that the distance from the nose of this horse, white horse, to the white horse over here is the same as the distance of this white horse to this white horse, this one, and so on. This is known as periodicity. You also see that this the occupation of these units are total in the sense that there is no empty space in this packing motif. So imagine now the horses, white as well as the red ones, to be replaced by molecules. If molecules are arranged in such a way that they have this periodicity, this is known as the translational periodicity, and this forms what forms a crystal. We can also have different orientations of the molecule. For example, in this picture, you see that there is a flying cat. It's a white cat which is going in the yellow cat which is going in the forward direction. A black cat goes in the backward direction. There is a twofold rotation between this cat and that cat. However, the periodicity is repeated and there is a packing. So essentially what it means is that we have these periodicity as a consequence which is present in crystalline motifs. It's arranged in a periodic fashion, and you see here different kinds of animals. And in fact, these. So if you look at another diagram, we can have more than one molecule, again arranged in a periodic fashion. And you see here different kinds of animals. And in fact, these diagrams are actually drawn by an abstract painter who had no idea of crystallography, but who had a tremendous idea of symmetry. And these are drawn by a person by name M.C. Escher. In fact, he recently passed away. And some of these diagrams are extremely useful to understand symmetry. You see that more than one molecule, different molecules, can come together and still generate a symmetric arrangement. Now, we want us to therefore study what holds these together. The way in which the molecules can be arranged can be also in 3 dimensions. And when we have this in 3 dimensions, crystals are built in a similar manner with regularly repeated cells. Only now these cells repeat in 3 dimensions to produce a box called the unit cell. So we have a unit cell which is defined in terms of 3 directions and 3 angles. It's a 3-dimensional solid. So if we extend this to crystals, we therefore get, based on the presence of symmetry and also the way in which we can arrange the boxes, there are only 7 ways in which we can arrange these boxes, and these are known as the 7 crystal systems. Most of these you have already got in your textbooks, but I thought I will revise that before we go into the actual discussion of polymorphism with relevance to the pharmaceutical materials. You see that here you have 7 crystal system. The systems depend upon what are the values of A, B, and C, and the angles alpha, beta, and gamma. So in a triclinic system, you see A is not equal to B, not equal to C, alpha, beta, gamma are not equal to 90 degrees, and this is the least symmetric crystal system you can have. As you increase the symmetry in the arrangement of the molecular species, the symmetry in the crystal structure also goes up, and you will get, therefore, 7 different crystal sites, and these are known as the 7 crystal forms. Now, what is crystal? This is a diagram which I like most because I created this diagram. This tells you what is really happening in a crystal. So if you consider a three-dimensional crystal as a loaf of bread, you see that the and so on, these will define, just a moment. So these will define the various planes, and these are known as the Miller indices. Now, just for the sake of clarity, where are the atoms? Where are the molecules? So what you do is you go to an Iyengar bakery and buy a special bread. And if you go to the Iyengar bakery and buy a special bread, you see that there will be added ingredients, like they will add badam, they will add these raisins, they will add cashew, and so on. And there will be pieces of all these inside the dough. So when the dough is mixed, it is not known where these ingredients are, but they can be distributed among various planes. You may be lucky that when you cut the central plane, you may get a piece of badam, you may get a piece of cashew, you may get a piece of raisin. But when you cut, let us say, a slice off here, you may not find any of those. This is exactly the way in which atoms are arranged inside the unit cell. For example, if you look at a plane in a crystal, which is shown here as a projection, you see that these are the additives where these pieces of cashew, pieces of raisin, and so on can go in. And this is exactly how the atoms arrange themselves inside the unit cell. So a loaf of bread is a very good example in which you can imagine the unit cell, get the imagination of the plane, and also get the imagination of where the atoms are. So just like you have done in this particular case, you cut the slice of the bread and then locate where the atoms are. You will have to now look at a situation where we have to find out where these atoms are. So obviously we can't take a crystal and then cut it to pieces and see where the atoms are because of the dimensionality that is involved. So what is to be done? We do what is known as a diffraction experiment. So we do an X-ray diffraction experiment where there are more than one type of atoms in the crystal. Each atom forms its own separate array, and each array separately satisfies the Bragg equation. So the atoms are located in different positions. Let us say this is the entire loaf of bread. The atoms red and green are situated in this way. The advantage of a crystal is that they are arranged in a periodic manner, and therefore we see the periodicity that is associated with each of these atoms. But what we measure is not the diffraction coming from an individual atom, but what we measure is the diffraction that comes from a plane. And those planes are marked in black here. The black dots represent the plane. The black dots, therefore, add the contributions coming from these planes, and this you can actually get the information about what is the content of this region of space associated with this point. 4 is represented by a point, and when you do an X-ray experiment using X radiation, you will get to these points. And these points will have differences in intensity depending upon the amount of that particular point. And that is what will give you a diffraction pattern. So these points, which are referred to as the planes of the crystal, are referred to as the reciprocal lattice points. So each reciprocal lattice point therefore represents a plane. So how can we see atoms? This is a very general way in which we understand how to see the atoms, because this is now required for us to characterize any pharmaceutical material and eventually go and characterize the polymorphic modification. Just a cross check. Am I audible? And is it clear enough, Priya?
Yes, sir, it is clear.
Okay. Is the voice coming out all right?
Yes, sir.
Okay, I will go ahead.
Yes,
so
sir,
how
your
do we
voice is
start?
audible,
We can
sir.
see it. Okay, thank you. Thank you. Let me go ahead. So how do we see these atoms? The way in which we see the atoms is we keep the object here. This object could be a piece of bread, let us say, in a microscope. And then you all know that when you send visible light onto this piece of bread, the scattering of light takes place in all possible directions. And we have a lens. And this lens now makes it into an enlarged image. And that enlarged image through the eyepiece, we again make a very enlarged image of the piece of bread. And the additives which we have in the piece of bread will show up as particles here. And therefore, we should be able to see and identify where the pieces of cashew and badam and raisins went in when we look into a microscope. So X-ray diffraction is also a super microscope. So when X-rays fall on the object, scattering takes place in all possible directions. And the scattering now is limited because of the symmetry. Tell you that several years ago, maybe 5-10 years ago, there was a change of many of the patents of drugs. And therefore, there used to be lots of industrial people standing in front of my office and asking me to verify and the new polymorph which they have made. It is not very easy that a new polymorph can be made. We'll see when we go to how we make the polymorphic modifications. So these are the three types of polymorphism. Now, why polymorphism occurs? It occurs because it's a question of the process of crystallization. When we bring molecules together, it brings approximately 10 to the power of 20 molecules or ions into a three-dimensional array. So it's a question of arrangement of people in a given lecture hall. Obviously, you have to have some kind of an arrangement. And so the crystallization process is also like a chemical reaction. It is kinetically controlled. The supramolecular reactions, where more than one molecule is arranged, is a thermodynamically controlled phenomena. And they have an equilibrium which is attained in supramolecular reactions, whereas crystallization is a kinetically controlled phenomenon. As a consequence, we do form different kinds of crystals of supramolecular assembly. Supramolecular assembly essentially means the assembly of different molecules governed by certain rules and regulations, which who discovered the first form of polymorphism is the year 1822, when a guy by name Mr. Relish published a paper in which he was actually looking at the following. I just thought I will read out whatever he wrote so that it becomes very clear to us what we mean by polymorphism. He says, whilst I was still seeking, I succeeded several times in the recrystallization of the phosphate in obtaining crystals having the same form as acid arsenate. So he was looking at phosphate and arsenate of a given acid, and he found that the crystals, when he recrystallized, they formed similar crystals. Since I knew that between the two salts, I proceed with the investigation of this phenomena, and the whole situation of the acid phosphate crystallizes several times in the form of arsenate. Hence, it is established that one and the same body, composed of the same substances in the same proportions, can assume two different forms. Arsenates had the same crystal form, and he defined this phenomena at that time as isomorphism. Remember, this is 1822. Much before the diffraction was found, X-ray crystallography was discovered. And so it is a remarkable finding for those days. So this is the first ever identification, in my opinion, of polymorphism. Let's now come to modern pharmacology, which is what is of interest to all of you. Problems faced in modern pharmacology. So the major problem of any drug is the issue of locality. So one has to work towards getting better and better results for solubilities as well as bioavailability associated with the pharmacological molecule. So one has to therefore design compounds with improved physicochemical properties and search for what we call as polymorphism. There are different approaches one can follow. We need not have only one molecule. We can approach it through multi-component formulations. These give rise to what are known as co-crystals, salts, nanoparticles, and eutectics. Co-crystal, as the definition says, is a crystal we make a crystal without a solvent. We can make a crystal without a solvent by melt cooling, or we can do what we know, which we practiced over the years, as in situ cryo crystallization. And in this particular case, diphenyl ether is shown as an example. What you do is take diphenyl ether, which is a liquid at room temperature, put it in a capillary, and mount it on the diffractometer, and then use liquid nitrogen to cool this region of the capillary. As we control the rate of cooling, depending upon the rate of cooling, and then we get to a crystal. The way in which we grow the crystal is by doing what is known as variation in rise. We heat and cool, keep on repeating that process. So eventually, by looking at the diffraction pattern, we can say whether there is a crystal which is formed inside this capillary. This is a technique which is very special and which is very unique, which we practiced over the years. And you see that the cryocrystallization of diphenyl ether tells us that depending upon the ramp rates, this was cooled at 10 degrees per minute, and this was cooled rapidly at 50 degrees per minute. and you see two different crystal forms which result as a consequence. And therefore, we can get to the generation of polymorphs. So this is another method by means of which we can generate polymorphs. So we can call this as the melt-cool technique, but this is a special technique. The temperature at which this has been crystallized is at the solidification temperature of diphenyl ether. One of the reasons why we studied this was to see and evaluate what would be the structure of a given solvent. In fact, diphenyl ether is a very common solvent which is used for crystallizing materials. So we wanted to know the nature of the solvent can influence, and that's the work which was then carried on. And we have been doing this over the years on several other materials. I don't want to go into the detail of it. On several other materials, I don't want to go into the detail of it. Another technique which we developed over the crystallization process is the use of what we call as vaporization. So what we do is we take the material and vaporize the material, and then we pass it through a narrow tubing, and then we have the temperature gradient which is set up across. And so this goes now, the sample is going from this vessel where we heat the sample, generate a temperature gradient, and it is now forced through, or a jet stream goes through here, goes on to a bigger volume, and then the crystal gets collected. Here, we go through this and vary the material. When you actually make the crystal structure, determine its structure, the structure of aspirin goes into this crystal form. So people try to make different polymorphic modifications in different solvent media and so on. And successful venture, which appeared in 2005, where they were able to crystallize the two forms of aspirin. So they wrote the elusive form 2 of aspirin has been obtained during co-crystallization experiment with levetiracetam or acetamide, and it has characterized by various methods. So they got two different forms, form 1 and form 2, and this was considered a very unique thing because people had not discovered any other form of aspirin. So aspirin was a very safe drug to take because it has a monomorph. But then when this headache of getting another form appeared, people began to worry about it. But however, in a later year, in 2007, this group, headed by Andrew Bond and Gautam Desiraju, showed that this form 1 and form 2 are in fact one and the same. So crystallography can be, therefore, sometimes a very challenging technique to use. So in this particular case, they showed that reducing and re-indexing X-ray data collected on a crystal of the well-known form 1 of aspirin in a unit cell recently reported for the new form 2 results in a data set from which the so-called new form can be obtained. That means form 2, if it exists, needs to be identified with more rigorous experimentation and modeling. Though they showed basically that the two different forms, 1 and 2, are one and the same. So it comes to a question of what is polymorphism? Does polymorphism is a reality or a polymorphism is a myth? Sorry. Well, polymorphism is a reality. Polymorphism can exist in different crystalline forms which can be prepared, and their pharmaceutical evaluation can be made in different kinds of ways. So polymorphism issues are resolved generally by using the following methodologies. One can use the PXRD, so three the differences, profile fit and rate field analysis are the approaches using powder X-ray diffraction. We can use the bulk evaluation using the DSC TGA strategy or the FTIR technology. And the supporting evidence can be obtained from solid-state NMR, Raman, and microscopic measurements. We can also do pair distribution analysis, and we can use charge density methodologies and the crystal structure prediction, which is another approach. And of course, the overall evaluation protocol is to satisfy FDA for approving a given drug. So once someone makes a crystal of a new polymorphic form of a drug, they go through these procedures 1, 2, 3, 4, and 5, provide enough evidence, and satisfy FDA to approve this as a new drug. So the same material can be now got in a polymorphic modified form, and that can be identified as a new drug. And the interest, therefore, of pharmaceutical industry is in this kind of an evaluation. But why polymorphism is an issue which is very, very crucial to explain. Why should there be polymorphism? See, we can always explain polymorphism in terms of intra and intermolecular contacts, the hydrogen bonding and other types of interactions, weak interactions, which hold the molecules together, the presence or absence of the solvent in the crystal structure, and so on. And these are all developed into what we call currently as crystal engineering principles and the way in which the energy landscape develops. And there is no reason to go into this detail in this informal talk. But we will try to see and ask why this polymorphism occurs, particular species, and the way in which these interaction energies develop when the crystallization process occurs. As we already saw, crystallization process brings in 10 to the power of 20 molecules into consideration when they come together and form the crystal structure. And therefore, the interaction energies involved among them is something which is very crucial in order to bring in the polymorphic aspect. So to answer why polymorphism, we looked at the curious case of acetylzolamide. It's a very beautiful experiment, and it was in fact, excuse me. This is in fact a very important concept which comes out from this study. The acetylzolamide, when crystallized from a boiling aqueous solution, if we rapidly cool, it goes to what we call as the thermodynamically stable polymorph. It forms a pyramidal NH2 moiety at the end of this. This is the NH2 moiety. The NH2 moiety, the pyramidal one, is formed in this context. So the NH2 is a pyramidal configuration. It goes to the planar configuration when we cool it slowly. And it so happens that this is the kinetic polymorph. That means we can convert this to this one through a methodology. The unusual phenomena of the formation of kinetic form as against the thermodynamic form upon slow cooling of boiling aqueous solution in case of this drug, acetazolamide, has to be rationalized. So we have rationalized it in known as what we call as the hybridization-induced polymorphism. Hybridization of the NH2 group that is present in the molecule will decide the nature of the polymorphism. Very interesting. Let's see how it happens. So this is the molecule. And you see the NH2 group up here. And the slow cool, as we already said, it gives us the kinetic form instead of the thermodynamic form. What do we mean by kinetic form and thermodynamic form? The thermodynamic form is the more stable one, and the kinetic form is something which is intermediate to the thermodynamic form. So in principle, it should be possible to go from the kinetically stable form to a thermodynamically stable form. Form is the more stable one, and the kinetic form is something which is intermediate to the thermodynamic form. So in principle, it should be possible to go from the kinetically stable form to a thermodynamically stable form, which essentially will result in the final drug. However, you see that when we did the slow cooling, the kinetic form gets formed, whereas the rapid cooling takes it directly to the thermodynamically stable form. So when we have rapid cooling done, we have the desired material, which could be marketed. So what is the underlying principle here? So the geometry, this was first observed by these guys, 1997. So we decided to look into it from what we know, what we normally do through what we use only the spherical part of the electron density. But what is more important and what is more relevant is the aspherical part of electron density, which essentially brings the molecules together. So the so-called interaction energies develop in the aspherical part of the electron density. So Halson and Coppens formulated this way in which one can calculate the electron density from the X-ray diffraction experiments. And this is what happens. Suppose this is a molecule which is under study. The crystal structure using the spherical part will give us this. These are known as, tell you, at any given temperature, how these atoms are vibrating at a given temperature. We can therefore do the structure at very low temperatures to reduce the spread of these so-called thermal ellipsoids. So having got this structural information, we can actually compute now the aspherical part. And the aspherical part will tell you how the distribution of the electron density goes away from the given atom. So effectively, the atom is taken out, and whatever is remaining after the atom is taken out is referred to as the deformation density. So this is how the molecule is deformed in this particular crystal structure. So you can see that if you consider this oxygen atom, you see the so-called lone pair. We always refer to as the lone pair in chemistry, and then talk about its reactivity and so on. We can actually see the lone pairs in some sense with the so-called deformation density. So this tells us the direction in which the two electron density regions are available. So any one of them could be now hydrogen bonded to the next molecule. In this particular case, you see that this is hydrogen covalently linked to the oxygen, And you see, therefore, the density associated with that region is reduced, and the lone pair now density, which is available, is shaping up outside, form an intermolecular interaction generating a given polymorph. So by varying these kind of reorganizations of the electron density, for example, providing hydrogen bonding potential in the other direction and so on, we can generate polymorphism. And that is the reason why polymorphism comes up. So in the case of the acetozolamide, we have calculated this using experimental density. And the diagram here, which is A, shows us the three-dimensional deformation density map. You see, this is the NH2 region. The NH2 now, the nitrogen, has a little tongue coming out that represents the possibility of accepting the electrons coming from the lone pairs which are present on this oxygen in the next molecule. And therefore, it is now ready to accept this. And if you see the form, this is for the form, the so-called kinetically stable form. And that's how it is readily formed. So in this form, we have the planar configuration. On the other hand, if you look at this term, you see that the electron density is now differently polarized. So blue represents the charge concentration regions, and red represents the charge depletion regions. And the Laplacian there is more detail of this. This is known as the Laplacian map. And this is the square of the electron density. So del square rho polymorphism. One has to do this kind of a work. This is something which will now unambiguously establish the reasons for why polymorphism exists in a given material. So having thus come to a stage where we have understood what is polymorphism, how polymorphism can be generated, and the third aspect of why polymorphism, we will now come to the other aspect which can generate the required pharmaceutical materials. That is the concept of co-crystallization. See, we discussed so far the single molecule or the given material B1. We saw at the very beginning of those colorful pictures that we can have more than one molecule that can come together and form a crystal. And the way in which these things do happen are illustrated in these two graphs. Suppose we take compound A, which is a pharmaceutical material. Compound B need not be a pharmaceutical material, but it could also be a pharmaceutical material. We can put them together and generate the dominance of addition. They adjust together, that means they come closer together. If we have a good additive property between A and B, we get to what is known as a co-crystal, where A and B are connected to each other. If there is no addition possibility, then we go to a physical mixture. And when we allow for a transition of a charge from A to B, by making use of, let's say, a positive region of the first molecule A and a negative region of the second molecule B, like, for example, in a hydrochloride salt, then it becomes a salt, which is again a dominance of addition. So I should have put here the salt as well, but that is something which is not so very critical in this particular example. The idea is to show that the co-crystallization definitely improves the physicochemical properties. This is the attempt to improve the physicochemical properties, because once we have these two together, the property, that is melting point, the solubility and so on, are shown to improve depending upon the way in which we have made these materials, known as a new technique. The easiest example which we can think of is the formation of alloys. So the eutectics are sort of, if not exactly the same, as alloy formation between copper and zinc, for example. So the two molecules are definitely existing separately here, because if one looks at the crystal structures or looks at the order diffraction pattern, it will look as though it is a physical mixture of A and B. However, A and B are weakly associated, and that results in a material which melts with a single melting point. And it's always that when we have this kind of a situation, the melting point is lower than the melting point of A and the melting point of B. And as a consequence, you can use these eutectics as a very clear possibilities for improvising the physicochemical properties of given pharmaceutical material. The way in which the molecules can arrange is shown in this possible diagram. Suppose we have we have a compound L, and then we have this polymorphs of this particular compound can be formed in different ways as illustrated here. You see that the polymorphs of solvate, or it could be salt, it could be a co-crystal, or a complex. So this is a complex of L with a dot. We can have different kinds of arrangements resulting in a polymorph. Suppose we have an isomorphous material which is like this, which is shown in green. Then we can form a solid solution of varying compositions. So differently varying compositions, which is illustrated down here as continuous solid solutions. Suppose we do form a solution which is discontinuous solid solution. This then defines what we call as a eutectic. So in this particular case, these two are isomorphous solids. They are similar solids, similar crystal structures, whereas these two are different kinds of solids, different crystal structures, but they can still form a discontinuous solid solution, which essentially results in a eutectic. So these are the futuristic possibilities of improving the physicochemical properties of a given material. The next one is, of course, the presence of nanomaterials. This is the last part of my talk. I think I'm reaching the allowed time limit. So the effective control of the particle size. So around 100 nanometer size nanocrystals may produce altered physicochemical properties. So there is a considerable amount of work which is going on in this context of making nanocrystalline materials of the given polymorph. And we also, of course, have new parts resulting in better solubility and bioavailability. In this context, we have developed printing methodology, which is the uniform particle size distribution. We're using a thermal inkjet printing. So industry wants as much clear as possible. So what we have done in our laboratory is to find a methodology by making use of this so-called thermal inkjet printing, which is essentially use the solution of the given polymorphic concept of thermal inkjet printing can be extended to 3D printing, so we can straight away get and print the till which is required. And this is the futuristic way in which one can approach the printing, and this process is very quick. The crystallization takes place in less than a few microseconds. And this is the big advantage, and we can look into that in more detail in the future years to come. So this comes to the last concluding part of my talk. I hope I have made an overview of, or a bird's eye view of the current scenario associated with polymorphism, and then brought out, I hope, the importance of these analysis of solids in terms of X-ray diffraction studies, single crystal powder, and the use of the bulk techniques like DSC, TGA, and so on, in order to establish and find out the answers to the three issues we question. What is polymorphism? How to generate polymorphs? And why polymorphism? So these three issues were discussed. A beautiful place. If you are by chance in Bangalore after the non-COVID days, God knows when it will happen. And when there is no COVID anymore, you are most welcome to visit our institute. And in this, I would like to acknowledge all my students who participated in this program, postdocs and project assistants. In fact, these are the guys who do all the work, and I just give the talk. Okay, and that is why I must acknowledge these guys with my heartfelt thanks. DST for funding the instruments, IAC facility. My JC Force Fellowship, which just got over, and currently I am an infra senior scientist. And I hope this lecture was palatable to most of you. And if there are any questions in this context, you can either write to me. I have given my email address, which is available on the very first slide. And if this has been recorded by any chance by Priya, you can provide this recorded message to everyone else so that they can have any questions which they would like to ask me. Very pressing, demanding question right now. I think we have enough time to have a couple of questions which we can answer. Thank you very much for your patience, and thank you very much.
So you have questions, huh?
Yeah, go ahead.
Questions, huh?
Yeah, go ahead.
Okay, sir. Two different molecules have same lattice parameter and space group. Is it due to preoccupied sites or something else?
If you don't mind, can you repeat it again?
Two different molecules have same lattice parameter and space group. Is it due to preoccupied site or something else?
Okay, you see, you saw the example of 1822. You saw that one was a phosphate, the other was arsenate. And both of them went to a similar crystal or similar. It is possible that it is essentially the arrangement, the crystal structure. And so it is possible. The question is, it will never be exact. You see, the advantage of crystal structure determination is the fact that we have the accuracy in these determinations. So even though the two cell dimensions and space group look very similar, they will not be exact. And that will bring in the difference between the two arrangements. So there is always a difference in the two arrangements if you have two different molecules.
So the next question is, what is difference between doping and composite making?
Okay. So doping is a methodology by means of which when we are crystallizing the material, we can dope it with a given element or a given compound. And the doping essentially takes this given material into interstitial sites. Okay, so that means it is not necessary that it has to go and occupy a given described position in the lattice. So it will remain the same, and the doping will now ensure the fact that this material is also inside this. Just to give you an example, if you take an inorganic material, just an example I'm giving. If you take, for example, the 1, 2, 3 sample, which is the superconducting material, and you replace one of the rare earth elements by a combination of two rare earths, depending upon the ionic size and radii, these go as dopants. So that is the difference between the dopant and the other issue which you have brought about.
So next question is, atoms give rise to molecules, molecules give rise to clusters, and clusters give rise to lattice, and then nanoparticles in this process.
Yeah.
Anything is released or observed.
Okay, very good question. Because once you have a nanoparticle, essentially, the concept of nanomaterials is based on what is known as asphalt ripening. So asphalt ripening will ensure the essential form a cluster. Unless a cluster formation occurs, asphalt ripening, as it is referred to, will not occur. And therefore, the nanoparticles, once they are formed, they remain stable.
So the next question is, in binary nanocomposites, is it necessary to have both individual in nanoscale, or is it enough to have one of them in nanoscale?
Yeah, and this is a good question in the sense that what do we mean by nanoscale is not very clear in this question. But however, when we have a nanocomposite, the nanocomposite is formed as a consequence of the association of the two moieties or whatever, more than two moieties which are involved in this composite. So when they come together, the association is on a nanoscale. So it does not matter whether they are, you see, nanoscale is already a factor of 10 times over the atomic dimension. The structures, the materials are in the angstrom units, and the nanoparticle is a factor of 10. So the consequence, this nano association can take place together. Both the materials, therefore, are in, to answer the question very loosely, are already in nanoscale.
So there is no more questions for you.
Okay.
Shall we move on to vote of answer?
Yeah, please go ahead.
Yes. Gratitude makes sense of our past, brings peace for today, creates vision for tomorrow. Give thanks for a little, and you will find a lot. The smallest act of kindness is worth more than the grandest intention. I am Ms. Monia Priya, Assistant Professor, Department of Biotechnology of Kapaganago College of Engineering and Technology, who I am the organizer of this workshop. It gives me a pleasure to deliver vote of thanks for this valedictory session of virtual workshop on nanotechnology and pharmaceutics of 4 days program. Starts from 3rd to hence by 6th of this month, organized by Department of Biotechnology of KVCD. First of all, I wish to thank our beloved patron, Dr. Meenakshi Annamalai, Director of KVCD, Dr. P. Kasinatha Pandiyan, Principal of KVCD, Dr. N. Subaraji, Dean of KVCD, Dr. V. Karthikeyan, Professor, Head, Department of Biotechnology, for their support and encouragement to do these developmental initiatives and activities. I would also record my sincere thanks to Dr. T. N. Gururao, Professor, Chemical Crystallography and Materials Design, Indian Institute of Science, Bangalore, for sharing very informative and wonderful session of your research expertise. Thank you, sir. On behalf of KVCD and Department of Biotechnology, I extend my heartfelt gratitude to all the speakers from day 1 session to day 4 session. Being in this lockdown, they find a time for sharing their research work. It's very informative and wonderful session. Thank you all. And I would also like to thank our energetic and enthusiastic organizing faculty team members for their timely support and guidance to make this event a grand success within a short period of time. Thank you all, my dear colleagues. I would also extend my grateful to our active participants, includes faculty, students, research scholars from various institutions from different states across the country for their support and cooperation. Thank you all. I hope that you all gained research information, techniques, and methodologies for your career. Finally, I would thank our biotech department students of KVC for all the sessions. Thank you, my dear students. Once again, I thank all all of you for your support and cooperation. Without you all, it could not be a grand success. Thank you very much. All your wishes to become a success. All the very best for your future. Thank you to all.